Hello, everyone. I'm Dylan Forsha. I work for Osberg, and I apologize in advance if you went to the Jug talk a few weeks ago. I did this talk, except it was in Java. I did do you the service this time of updating this to Scala, so there's a little something in there if you want to watch again. Okay. So we're going to talk a little bit about the actor-based model of concurrency. We're going to talk about how the traditional concurrent programming techniques have a few issues and what those are and how actors are a solution to that. We'll also talk about how Akka's motto is "Let it crash" and what that means. We'll talk about how to reference actors. And then finally, we'll talk about where actors are deficient and what the next steps are to resolve those issues. So for traditional concurrent programming, you typically think of doing locking mechanisms, either directly using a mutex or a semaphore in order to lock and unlock around an area that you don't want to access some data structure at the same time with two threads. Or if you're using Java synchronization, you can lock on a monitor. And the way that works is you go and lock, and then that lock is called a monitor. And then whenever some other thread has done some work so that you can go and continue on your way, you can get notified with a signal that it's done so that you can continue on your way. So you have either the option of waking up one thread or waking up any threads that are locking. So there's a few problems that you can run into with this kind of concurrency model. First, most obvious one is deadlock, and that's where you have this circular dependency of threads that are each waiting on each other, and nothing ever happens, so you're just stuck there waiting. The second thing is live lock, and that's where two threads are kind of reacting to each other's monitors or mutexes, and they're never getting anywhere. They continue on, they just can't get any more work done. And then the final thing is starvation, and that's when one thread may never have the opportunity to go forward and make progress due to another thread either taking too long or other threads making it in front of it because they have higher priority or something of that nature. So kind of the traditional way of thinking about these kinds of problems is through the dining philosopher's problem. Has anybody here heard of the dining philosopher's problem? No? Okay. So go to an example here. Actually, we'll look at the picture here real quick before I do that. So you see that, let's say that you have your 5 philosophers sitting around a table here, and they each need to go and eat some food. In this case, we'll say they're noodles that they're each trying to eat. And in order to eat those noodles, they need to pick up a left fork, pick up a right fork, and then they can go and scoop up their noodles. But the thing is, you see here that, that each one of these philosophers, they share their right fork with the person to their right, and they share the left fork with the person to the left. So what can happen is, you know, you can end up with a deadlock if all of them go and pick up their left fork and then go up and pick up their right fork, and you know they are philosophers, so they're thinking in the middle, doing some kind of work in their heads, and you can just get into a cantankerous situation. So as a demonstration here, you can see that we'll set up a set of monitors here for each one of our 5 forks that are sitting between our, in this case it's actually, no, it is 5 philosophers. And so the first philosopher here, we'll name him Plato. He'll be assigned to fork 1 and fork 2, and then Socrates gets fork 2 and fork 3, and you can see how that goes and models things around in the table. So you see for each philosopher here, he starts up a thread, he picks up the fork, which in our case just means that you're locking on your monitor here. You do your work here, and then you try to get the right fork, and then you do your thinking here, and then you put it down and put the other one down. So if you have the whole circle here, you see what happens when you run it. So you see they all pick up their fork and are thinking, but, well, they're now stuck there. They can't make any progress. They're all just sitting here looking like they're idiots with one fork held up in the air. So if you go and break this cycle here, just remove out this guy. He's only needs one philosopher is come up with a brilliant realization that he can pick up things with just one fork. So once that happens, you see that you run it, and they all put down their forks, and everything is okay since you no longer have that cycle here. So that kind of describes a deadlock and shows it in action. Live lock would be a situation where you try to overcome your cycle here by, say, all of them going and, after not being able to get the second fork, let's say that they all go and put down their left fork and then wait for another half a second and then go try to pick it up. Well, you're going to get live lock because now they're going to get in a little dance here where they just all keep on picking up their left fork, and then their right fork always disappears at the same time. So see that they're all kind of in a live lock there. And then with starvation, I guess it doesn't really describe that, but we'll see in our actor example how you actually can't necessarily solve the starvation problem or the live lock problem with actors. Deadlock is the main thing that you're trying to fix there. All right. Okay, so how do we simplify this situation? So how can we get rid of those monitors and locks, or at the very least abstract them away? What we do is we create a queue, and we're going to call that a mailbox in actor parlance here. And that's just going to be full of messages that an entity called an actor will process single file. So you get your concurrency by just having multiple editions of those actors there, that each one can be a thread, but they don't compete with anybody else. The locks are kind of encapsulated inside of the mailboxes there, so you don't have to worry about it anymore. Something very important to consider here is that your mailbox of messages needs to be full of messages that are immutable, because if they're not immutable, all of a sudden you've got two threads that can look at state that can change out from underneath them. So that was a little bit harder if you saw my Java talk to do it there, but the nice thing about using Scala is that you have a great set of immutable data structures that assist you and make sure that that fact is indeed true. So a little bit of theory here. Your actor can make local decisions, which means that if you've got some kind of internal state that your actor needs to modify between messages, you're free to mutate that at will. The only way he's communicating with the rest of the world is through messages getting sent to him, and he's processing those messages single file. No two threads are going to modify that state at the same time. The next thing is that you can send a finite number of messages to other actors. I think the key word on is finite here. If you send an infinite number of messages out, well, you're never going to complete. You'll cause starvation there. You can also create a finite number of new actors. So typically you'll go and break down your work a little bit more until it's a reasonable size, and you can just create actors at will. They're very, very cheap. I'll go over that in a few minutes. The last thing you can do is you can designate a behavior to be used for when the next message arrives. So if you know about a finite state machine, it kind of models that. You can go and say, well, I'll send out this message, and then I expect this kind of response to come back, so I'll switch out my behavior so that I'm expecting something else at that point. So the example I'm going to use for a parallel algorithm here using actors is a merge sort. Who here knows how a merge sort works? Okay, good section of people here. So a refresher, if you don't remember, it's a divide and conquer style algorithm. So let's say that you have this particular array here, 9547. You can sort that by dividing that guy in two, and then sorting each half of that guy, and then you can divide each of those in two and sort each of those guys. And by definition, an array of size 1 or 0 is sorted already, so you're sorted at that point. And then once you sort the subarrays, you can kind of imagine it like you have two sorted decks of cards where, you know, on the top you've got the least element, and you can go and take two sorted arrays and merge them together very, very efficiently by just taking the least of the two cards and then kind of flipping them up, and they'll end up in order, and it'll be an order in operation. So you can see that algorithm, since you can divide out this work, is pretty well suited to parallel algorithm. As it turns out, if you try to compare this against the built-in sort, I think there's a lot of high constant factors here, so probably not a really good idea for most practical applications, but it gets the point across for this. So let's imagine how we'd model this with actors. So let's say that you have a sorter actor. He gets a message in for a list to sort. He can go and create two more sorter actors here, and each one of them is handed a message with half of the array, and then they do their thing, and they can keep on splitting in half here in order to delegate authority here, and then they respond back up the chain, and then it all gets merged together. Just for the sake of modeling it, the merger was pulled out into a separate actor here, so he'll send a message over to the merger saying, hey, go merge these two guys together, and then he gets the result, and then whoever was the original caller gets your final result. I mean, these are each one of these blue boxes here is a separate actor. So you might be thinking, that looks a little bit familiar here if you've ever used any kind of message queuing middleware. It kind of looks the same, that you just got processes out there and you're sending messages between them. Or if you're familiar with the Java executor service, you can submit jobs in a queue to that, and it works them off by pushing things out to a thread to work. There are some differences, though. The first is that you can dynamically spin up child actors easily to go and subdivide the work down. You have a mechanism to perform failure recovery, and I'll go over that in a few minutes. And the last is that you're free to perform the work either locally or remotely, and I'll also go into that. So if you're doing it locally, it's all just passing references around, so that's pretty quick, but it's also got the ability to serialize it and send it over to a different machine. Well, with the future, the future is pretty much like an executor service. I mean, it's just kind of a nice overlay on top of that. So with the futures, typically, yeah, you'd go do something like a map or something like that to chain together operations, or you could sequence them together. So a lot of that will be similar. I guess probably the big things are the second two items here, the failure recovery. Like you've got a way to like go and restart sections of the actor system based on policy, and probably the bigger thing is that you can do remote concurrency with this. With the futures, you're pretty much stuck on the same box there, but with this, you can horizontally scale. Akka actually has a whole clustering system if you want to go learn more about that, to dynamically add more machines to the cluster and distribute work across it. Yes?
I'm not sure, so I'm going to ask you. It occurs to me there's a big difference has to do with that mailbox. What's in the mailbox?
So I'll go over what the mailbox is in a bit, but you've also got various options for your mailbox there that you can let messages drop if you're just trying to keep up with the real-time stream. You can block on the other side. You can throw an exception, there's various options there on how to deal with it. And also you can share mailboxes between actors in some cases. So I'll actually go out into that in the details in a little bit. So the nice thing is that actors use thread pools underneath the cover. So you only really need a thread as long as it takes to process one single message. So the thing about that is you got to be careful not to block in an actor. Because if you block in too many actors at the same time, you've consumed your entire thread pool. Nobody else is getting work done. So the way that you typically deal with that is you break down the work and send it to child actors. Child actors are very cheap, so you just try to get it down to a small enough chunk of work that it should happen in a short amount of time. Now for I/O, you still got to be a little bit careful there because there's really no way to keep that from taking a long time usually. So Akka gives you a way to assign a separate thread pool to an actor or a set of actors so that you can use it just for those operations. And actually for Scala, I think you can also use this with the futures where you can put a blocking block in there, and that'll tell the thread pool, hey, you can go and fire up more threads to handle actors if you're using a fork join thread pool underneath the covers. So, and that's the default thread pool, so that's one way around it. So you're free to create lots of these actors. They don't directly create a thread, and they only have about a 300 byte overhead per actor created. So you can have thousands, or in a large system, even millions of these running simultaneously in a system. So if you compare that to just creating a bunch of threads to deal with this, each thread needs to allocate a thread stack, which is 512 kilobytes by default. So you're several orders of magnitude larger in size. And the other thing is, if you've got a whole bunch of threads, you're going to kind of bog down your machine with context switching between all your various threads. If you were to have just a certain number of actors that are doing a chunk of work, it's always going to have about, maybe 2 times by default the size of the number of CPU cores you have, and so it keeps your context switching to a minimum. So for talking between them, this is you've got a whole selection of mailbox types here. You've got non-blocking mailboxes. That means that on the send side, things will always succeed. You just go and fire and forget that anything ever happened. And then the blocking means that it'll wait for a timeout to happen. And if you can't insert it, you'll get a failure with an exception coming out of your send. On the non-blocking side, you have various options. An unbounded mailbox, that just means that your queue just keeps on growing indiscriminately. Of course, you got to worry about out-of-memory errors if you go that route if you're not careful. You can have a bounded mailbox where after the timeout, if it's not working off quickly enough, you'll get an exception. You can assign priorities to it. You can send control messages, all sorts of good stuff there. So for the blocking, got a lot of similar things to the non-blocking, but you're going to be blocking on the send side. So how do these Akka actors work? Well, in the simplest case here, you just have to extend from an actor class here and define a receive. And then you just apply it a partial function here for the messages that are coming in. So this is kind of an example from the merge actor. So you detect that a merge came in here that has 2 lists that it wants to merge. And then you can go get whatever actor it was that sent the message. That's kind of passed through an implicit whenever you call tell, which in Scala is this nice exclamation point operator there. And then here is where it's going to generate what it's going to send back right here in this perform merge. So you can match on the object coming in, perform some action, and then you can also swap out this whole receive method by just calling become and passing it a different receive object here. So I'll show you some example code with that in a few minutes. So to reference an actor, you need to be able to you're going to need to be able to find these things, of course. You can either get a reference to it upon creation. So kind of the root of Akka is this actor system object here, which is pretty simple to create. You just create one with an apply method, give it a name, and then you just call actor of, and then typically on your actor, you supply this props method, which will then go and give the parameters that you need to go and fire it up. It's generally considered good practice to create those in some kind of static method in the actor class. I guess this is for my Java talk here. It's going to be in your object for the class. So besides on creation, you can also look up actors, and whenever you create, so besides being able to go and create things from the root actor system, you can actually do there's a context that you have in scope in your actor that you can go and create a new actor with the same actor of method here, and it'll create that underneath the tree of actors here. So when you're looking one up, it looks pretty much like a directory tree here. Over here, this means that you have actor A, that created actor B, that created actor C right here. So you can reference that embedded actor there by putting a path. And just like directories, you can do relative paths. You can use .. / So if you're an actor C and looked up .. / actor B1, you'd get the sibling of actor B right here. So something important here is that it's returning an actor ref, not an actual actor instance. And this is important later when we talk about remote actors. It's kind of an indirection here so that when you're programming, you won't have to worry about whether an actor you're delegating work to is local or spun up somewhere else. So you've got a couple of different messaging paradigms. You already saw the tell, which is the fire and forget here. So if you just take your actor ref and exclamation point foo, it just sends a string foo to the actor and then continues on its way. Kind of an implicit right here, like I said, is that yourself is put in as the sender for it, and it's passed along the way. In addition, you can also do an ask, which is conveniently a question mark right here, and that will return you a future object. So I think you were asking about futures before. They actually interoperate with actors. You can use them in combination, and with the ask, it even returns a future for you. So you can, if you know what a future object is, you can take the result, do all your standard mapping and flat mapping and sequencing and anything that you want to do with that guy. You can also call a .get on a future, but that's generally discouraged unless you have to, because now you're blocking at that point. Point is to try to avoid that if possible. The last thing you can do is forward it, so that's kind of useful for things like routers. You can just get a message and go and tell it to go on to another actor, keep the original sender of that message so that it knows to go back to the original guy and not you. So pretty similar to a tell, except it keeps the original sender. Are they immortal? No. No, you can, I'll go into that in a second. You can go and tell them to kill themselves. Quite literally. Yes? No. Oh, yes. Yes, actually that's a good point. This whole thing is actually inspired by Erlang and its whole concurrency system. Yes. So yeah, so if you've used Erlang and its concurrency system, think of this like Erlang's concurrency system on top of the JVM. So yeah, very, very good point there. I think I brought that up at the beginning of my Java talk. I just forgot about that. Thank you. All right, so in addition to being able to send and receive and create actors, you have a whole mechanism to handle failures. The whole motto of Akka is let it crash. It means that you expect failure and just provide a means to recover from it. So this will help you create robust systems that keep on going on even upon failure. So For the failure monitoring, you have a few different options for supervising your children. So yeah, each actor is responsible for either handling a failure of a child or escalating that failure to the next guy up in the tree. So your options are either you can resume the subordinate, say keeping its internal state. You can restart it, but create a fresh version of the state for it. You can just stop the subordinate permanently if there's a problem, or, like I said, escalate, just pass the buck, kind of like exception parsing. Yes?
Is the failure and error networking escalation, does it take place in the same message buffers as your main program, or is it a separate pipe?
I think it's a separate pipe. I wouldn't swear at that though. Yeah, it's not. I mean, it doesn't look like it's coming from the queue. You'll see in a second what it looks like to create a strategy for it. Yes, exactly. So it's going to be like exceptions that you're dealing with here.
Does this implementation of the model have the top-level supervisor that's all it does is supervise?
Yeah, I believe there's a root supervisor for this. I think that's your actor system object is handling that. And I think through configuration you can kind of set up what he does. I could be wrong, but yes, there is a root. There is a root to this. Yes. So you've got those actions, and then you have two different strategies for how you'll deal with all of your children. You can either do a one-for-one strategy, which means that these actions only apply to the child that failed, or you can do an all-for-one where you apply to every one of your children. And you can actually determine the appropriate option based upon which exception was thrown. And that looks like a nice partial function again. You just, in your actor, you define a supervisor strategy here. You can define like the maximum number of retries within a certain period of time, so you're not spinning your wheels. And then you see here that if you get an arithmetic exception, you should resume, null pointer exception, restart, etc. So pretty concise, easy to understand, I think. So in addition, you also have router actors, and Akka provides a good variety of those out of the box. The ones that are named with pool in the name typically means that it creates its own set of actors, and you just give it like a class name in order to do that. And then a group means it's supplied a section of actors in order to route to. So some examples are you can have a balancing pool that creates multiple of an actor that share a mailbox, so that whoever's free next just takes the next item off the queue and works it whenever it's available. You can do a round-robin distribution among actors. You can have a strategy where you pick the one with the smallest mailbox, the least amount of outstanding work, or you can actually broadcast a message to a bunch of different actors. And this list isn't complete. There's a whole bunch of them in there, but these seem like a good section of commonly used ones here. And these router actors, you can define them and configure them via configuration, so you can change them up on the fly. So remote actors, like I said, you can run actors on a number of different machines. And when you send messages to an actor on another machine, that actor is abstracted away locally behind one of your actor ref objects. So importantly, this means that you have to create all of your calls as asynchronous, possibly having a long response time, because it could be shipped off to, across the country, I guess, if you set it up that way. And you can even set up, you can actually take an actor reference and serialize it and send it across the wire. So, if you want to go tell somebody on the other side, hey, go send your response to guy number 3 over there in a nice little triangle configuration, you're free to do that as well. And you can use your same actor selection that you did before, except you have to add a few things on. You can say Akka dot, you can either use TCP or UDP to talk to them. And then you have to give the name that you supplied your actor system at, the host name it's at, and port that you configured it on, and then that same actor path at the very end there for the remote system. And you can actually configure in your configuration file which particular machine an actor will get spun up on whenever you create it. And I'm not going to go into this today, but there's a whole clustering mechanism where you can dynamically go and distribute among machines that can dynamically add themselves to the cluster. So I'd encourage you to look into that if that's of interest to you. So a nice thing is that Akka provides support out of the box for Google protocol buffers for that serialization. If you send protocol buffers messages between remote actors, it will transparently serialize and deserialize that message over the wire. From personal experience, if you think that two actors might communicate remotely, it's probably a good idea to wrap it in something like protocol buffers out of the box so that you can just dynamically go and start doing that. You can freely move those actors via configuration, and also it enforces that immutability constraint, which with Java that was a little bit more important because you didn't have all the nice immutable data structures you have in Scala, but still, once you build a protocol buffers object, it's set in stone at that point, which is very important for actors anyways. So got all sorts of configuration options. You can set up the properties of all the mailboxes of your actors and configurations. You can set up your routers, remote actor system locations. You can set up how thread pools are configured and refer to them within your program. And there's lots more things. So it's a very configurable system. So we'll go here and take a look at what our merge sort looks like with all those pieces put together here. What you see here is that you're going to create yourself an actor system right here. You gave it the name sort. If you remember, that's when you're doing an actor selection on a remote actor, that sort is part of the URL that you have to give it to refer to it, so that's important. And then to create your sort actor, you call that actor of right here. You give it the properties right here. Oh, yes, sorry. Is that good? Okay. So we're going to generate a random list to sort here. We're going to use the ask here so that you send off your sort request. And then on that future, when it completes, we'll go and get that result out of it, go print out that it's sorted, and then terminate the actor system so our process will go down. So if we dig down here into the sorter actor, you can see that we define our messages here as nice case classes in this case, since we're not doing remote actors. It's a quick way to create messages. So you send it a request to sort a list, and then you get a list back. They're technically the same thing, but we've got our type information here, so we know whether it's a sort or a sort result that's coming in. And we handle both of them, so that's important. So our properties here, we just have to run and apply with no arguments right here, because in this case we don't have any configuration that we're sending to it. Otherwise, you just have a parameter list that would go and get sent into there. So for our receive, we're going to define that to initially be idle here, and our idle is just sitting there waiting for a sort request to come to it, and then once it gets that sort, it'll go here and perform the sort. So importantly here, we have to keep track of that original parent here because we want to go send our final response after getting all of our information from our child actors back. And right here, I put a sequential sort limit here. So we can just set that to 1 if you want it to go all the way through a merge sort. And otherwise, you can kind of get rid of some of those constant factors by going in and sorting lists of 100 and then merging them. So if you've got a list of 1, you just go and return your sort result to the parent. It's already sorted. No work to do here. Otherwise, what you do is you create 2 subsort actors here. You'll just go and split the list right down the middle right here, and then you tell the first actor the first half and the second actor the second half. And then we use our become here in order to wait for the results to come back. So if you go down here, you see that we're just waiting for a sub-sort result right here. So if we don't have a first sort result here, we're going to go and store it off here, and this is safe to do right here. You can overwrite that at will because you're in one thread there. And here's your poison pill. Like I said, you quite literally kill them. You send it a poison pill message, and then that actually does go into the queue, and then it'll work off any messages it has, and then once it gets to that poison pill, poof, disappears at that point and ends. So once you get the second result here, you go clear out your first sort result here. You go and create a merge actor right here, send your two lists to merge right here, and then you go wait for a merge at that point. So you just get a merge result there. All that guy really does is just kills the merge actor right here with the poison pill, and then returns the result to his parent. And then since he's not really expecting any messages to go out right now, he sets his parents to dead letters. And dead letters is just kind of like no man's land. You can send messages off to the actor system has an event mechanism. You can go and monitor those, and it logs them. So it's a way to keep track of things you didn't quite expect. And then at that point, it becomes idle again and waits for another message to come in for another sort. So if you go back to your merge actor here, looks very similar. You've got this, you just send a merge result back and perform the merge. And here's your nice tail recursive merge algorithm. Like I said, you have two lists, and if the first item is less than the second one, you pick that guy out. Otherwise, you pick the other one out, and you keep on pulling those out until you get to the end. And then once you cleared out both lists, you can go reverse it, and got an in-order merge list right there. So we go here, you can see that we've got pretty big list here that we want to go and merge. So if we go and run him, takes a little bit trying to put a sorted list in, or an unsorted list in, so it goes and checks to see if it's sorted, says it's not. Then you wait for a little bit. Then 10 seconds later, you've got a result that is sorted. So we run that guy again here. Wait till it generates a list here. You can see over here that he's pounding my 8 virtual CPUs on my machine, going and merging. It took about 10 seconds again. So as an example of what you can configure with your file here, you can set up your default dispatcher right here. I've got 8 threads assigned to him. If I go in here and tell him that there's only 1 thread available to him at this point, you'll see that this guy should take quite a bit longer to run at this point.
So when you create an actor and it gets an actor reference, is that just a bit? Is that what it is, or is it, how does that handle that?
I mean, it's going to contain your entire actor path inside of an actor ref when you get it. Because, like I said, you got to serialize that guy if need be. So if you put him into a message, you can go and grab that out of there, and then you can go back and reference him from somewhere else. See, it took slightly longer this time. You know, it's not a completely parallel algorithm, but gets the point across here. All right. So does anybody have any concerns about this?
I'm still swimming in the
do we have what?
I don't. It's the entry point. I got that, but I'm like, what's different about it than?
It's just like a way that you can reference the initial state. Like idle is, that was just a construct that I used. You don't have to make an idle. All you need is a receive.
Its job is to say, here's the messages I'm going to get and what I do.
Exactly. So the reason that there's a separate idle defined there is because, you know, you're going to go through a whole like circle of receive methods, and at the very end you want to go back to where you started. I guess you could just call receive, so you could get rid of that probably. Yeah, so you could just do a become receive at the end instead of even having an idle. So yeah. So let's see here. What was that? Oh, sure. All right. Ah, yes. Yeah, so you got your actor system, create your actor. We create the list to sort. I've got a lot of stuff just to do metrics on it mostly. Oh, is what?
I was curious how you're killing the actor system.
Oh, yeah, there's a...
One of the ways that happen whenever I have a self-creating application is that actor system doesn't always shut itself down.
Gotcha, yeah. I think that's a typical problem that you got to be very careful to make sure you shut it down, or else your process just hangs there and never stops.
Or you set the way that it creates a statement.
Yeah, that's true too. You could do that. But in a lot of cases, you want to make sure that things are flushed out of your queues if possible. So in those cases, that might not be such a good idea. What was that?
It's also good remote execution. It's like it's not just a matter of getting ready. You have running on those boxes.
Yeah, I mean, I think what will happen then is that whenever he tries to do because an ask is basically like two tells going in two different directions. That actually brings up a good point that you've got to, whenever you're setting up like a set of machines that are using actors, you got to make sure that each one of your machines is on the same network and that you can directly reference it by IP. You can't have them hiding behind NAT or anything because you have to be able to refer to that machine. Huh? That's a good question. I'd have to look at the documentation. Maybe, I don't know. Yeah.
So there's a serialization. How robust is the message language? Like, what kinds of messages are you allowed to send? Can you send a message that has arbitrary code in it to be executed? Are you supposed to be just stateful messages, or?
So, yeah, in one of the earlier versions of Akka, they actually let you send code across the wire, which, of course, is a terrible idea from a security standpoint. At this point, you got to make sure that whatever actor that you want to go fire up in a different box that is his local jar file has to have that guy available to him. I think that you typically want to keep your messages fairly short, because otherwise you'll be blocking up the network pipes if you're sending things remotely. I forget what the default size is, but in the configuration you can limit the size of the messages that go across the wire. Otherwise, yeah, just make sure it's immutable.
Right. Then what kind of diagnostics tools are there available to like inspect an actor while it's running?
Good question. So does it use JMX under the covers or something of that nature? Cool.
You talked about supervisors having
Yes.
What strategy did you use in this case, and what was your rationale for using that strategy?
Well, this is just using the default strategy, which I think is just, I think it's resume. So if you had some kind of error, I think it just goes and like restarts it, and then with its state intact, and then it just continues on its way. This is just a simple example, so I don't think there's much of a need to worry about that here. Yes?
In the other cases, you just had, what do I do with my children actors in the strategy? Can I also send messages or do other things when they're done?
Should be able to if you wanted to. I don't know if that's good practice or not, but I mean, as long as you can go grab a hold of an actor reference, you can do what you want in that block. So I think Akka itself actually has an event bus that as things like go up and down, you can go and register for those events if you care about them. All right. So kind of an issue here with the actors is what happens if an actor is performing work much faster than an actor receiving messages from it. If you had a non-bounded mailbox, you could get out-of-memory errors. If you're using a bounded non-blocking mailbox, you could just lose messages in there. If you're using a bounded blocking mailbox, you could have exceptions thrown to you, and well, what do you do about that? We need something that's called back pressure here to handle that. And Akka Streams is a kind of a layer on top of actors that gives you that ability. So you've got what's called a flow there, and it'll process each of the messages, and then it can send demand information upstream to upstream actors so they can go and slow down if downstream actors aren't keeping up. So this makes it so we don't overflow mailboxes along a big chain of actors here. And it's important to note that actors out of the box don't have this functionality. Unfortunately, Akka Streams doesn't yet have, or possibly never will, I'm not sure, have the ability to work across machine boundaries because those demand messages could get lost if it's remote, since it's just a sequence of tells. You have no idea whether it actually made it there or not. So this underlines the fact that remote actors have at most once delivery. And actually, my colleague Jordan Palmer, he's in work right now on an Akka Streams presentation. I think he's going to give that at JUG. I forget if it's next month or the month afterwards. And presumably, he'll probably give that same talk here if you don't get a chance to see it there. So he'll go more into that. So seems people are already asking me questions, but open it up here for any more. Yes?
A lot.
Yeah, yeah.
So the Akka stream seems really, really neat. Can you blend the two approaches so that you can have like Akka streams on one computer and then send a message to an actor on another computer and then start a new streams process?
Absolutely, yes. Actually, on the Akka Stream source, which is where like messages start in a whole graph, there's an I think it's, what is it, actor of, not actor of. Well, there's a way to like create a source that's based on an actor. So you can just say, well, start up an actor, and if you know Akka Streams parlance, that's like the materialized value for your flow. And then if you send messages to that actor that comes out of it, they'll go and continue on through your flow there. So yes, you can mix and match them. That's a good way to get around that remote consideration. Anything else?
Okay.
Yes.
So one thing that whenever I'm working with GPU systems is always really hard is, first of all, trying to figure out like what's going on where.
Yeah.
Just sort of the dynamics of the problem. Like what, other than, runtime inspection, like how does this help with that? Or are there other tools built around it to help with that?
I mean, just from a development standpoint, I'd say like At least with the Akka streams, you're able to kind of like break things down into chunks so you can go and you know, make sure that they're working individually. There's the Akka event bus that you can hook into to see what's happening there. I guess since you've got firmer control over what actions are taken when things fail, you can have some insight there. I mean, otherwise, yeah, you're depending on things like JMX to go and introspect it. Yeah. All right. I guess that's it then. Thank you, everybody. Now, I'll get these slides and the code sample posted to the